Okay, I guess let's get started. Thanks everybody for coming to the SIG Instrumentation deep dive. In case you missed the intro, it's recorded, but just a very general overview of SIG Instrumentation. We're basically responsible or in charge of the instrumentation pieces in Kubernetes. That doesn't necessarily mean we own all the lines of code that do metric or log or tracing instrumentation, but it means that we provide the best practices and guidelines for the project, for other SIGs to hopefully comply to, and frameworks for these things. And if you want to know more of the basics of that, check out the SIG Instrumentation intro. We're at the deep dive here, and actually Max is going to be talking about one of our sub-projects. I'm not actually part of this session, even though I'm kind of in the schedule, but take it away, Max.
Cool, thank you. Thanks. All right, cool. So after this introduction, thank you. I want to talk about optimizing metric rendering in kube-state-metrics, which is one of the components of SIG Instrumentation. And I'll go a little bit into what that is and what that means and so on. Mostly metrics rendering from the perspective about like the Prometheus metric format and how we can do that in a very efficient way. So how can we performance optimize metric rendering, so in the end, string interpolation in a very efficient way. Cool. For myself, I'm Max. I'm part of Red Hat. I'm part of the Prometheus upstream team as well, so I'm one of the maintainers of Alert Manager, for example. But also I'm very connected to the Kubernetes world, so whatever connects the two worlds, I'm working on a bunch. Yeah, cool. All right, so we already saw this slide. Optimizing metric rendering of kube-state-metrics of that very specific component in SIG Instrumentation. But you could also take a different perspective at this talk or look at it differently. Maybe you're not very interested in kube-state-metrics, for example, or that particular component, or you're saying, okay, it's performance optimized now, like, cool, I don't really need to know about the internals. But the alternative perspective you can really have here is, how can I performance optimize an application with the help of my monitoring system on top of Kubernetes? So we'll do that with the example of Prometheus, but that, of course, could always just be any other monitoring system. And what kind of metrics do we need to look at for? And how can we do that in a very efficient and iterative process? Right. That is the other perspective, but still I'll look at it at this perspective of kube-state-metrics. So whoever heard of kube-state-metrics? Right. Who has ever used kube-state-metrics? That is cool. Okay, perfect. All right, so we have a problem that we want to solve with kube-state-metrics. We have the API server on the one hand. The API server, or Kubernetes in general, has a bunch of state that is mostly saved inside of etcd. And we want introspection into that state. We want observability into that state. And we don't only want snapshots of that state, but we also want that in history, like in a time series manner. Kubernetes is very nice. It gives us a great API on top, but it can really only give us the current view. And it also only gives that to us in the end in a RESTful manner as Kubernetes objects. On the other hand, we want to funnel all of this into Prometheus. Prometheus as a time series database, or really any of your monitoring systems. This expects a certain format. So in object-oriented programming, this would really just be the adapter pattern. In Prometheus, this is called the exporter pattern. So we need something in between the two to translate between. And that would be kube-state-metrics. Here's like a small scenario. You have the API server. We use the watch API, notify us that there's a new pod. We take that pod, we cache it inside of memory on kube-state-metrics. And then asynchronously or not in line with that, Prometheus comes along at some point, tries to get all the metrics. It's on a pool model, so it does a request. Kube-state-metrics iterates over its entire cache, takes every pod, looks at it, generates the metrics out of those pods or config maps or whatnot. and then returns the metrics as. And in the end, it's a byte slice on Golang, but yeah, anything really. Cool. This is the architecture of the old version. The overall idea stayed the same. It's still the adapter between the two, but the internals changed quite a bit. So I refer to the old version as the not so much a performance optimized version, and with the recent performance optimizations, that's the new version that we're going to talk about. Cool. A little bit more like what do we actually cache, or what am I talking about when I talk about Kubernetes objects? You all know the YAML representation. Here, for example, you have a pod, all that info that you would get from the RESTful API, and on the bottom you see a snippet of the metrics that we would generate out of this. Like, for example, we have a kubepod container info metric, which tells you the container name, namespace, and the pod. And you really see the data matching. Like, it's really like traversing one data into some other. In general, kube-state-metrics doesn't do any heuristics on the data, but tries to give you the raw data so that you can do all the calculations and analysis inside your monitoring system. That makes you most powerful on that end. Right, so we cache the Kubernetes object, and we return the Prometheus metrics to Prometheus in the end. Now, all of this worked quite well. Actually, I can go a little bit back one more time. All the communication between API server and kube-state-metrics was entirely happening via Kubernetes client Go, and then all the communication between kube-state-metrics and Prometheus was entirely happening with Prometheus client Go. So we promptly just had to change the prefix, and all of it was just figured out for us. Now, we had some problems with this design. It worked quite well over time. But long-term problems were on bigger clusters. We're talking about something like 50 megabytes of metric output or higher. So that's, I don't know, our benchmarking clusters were at least 250 nodes, constantly scaling workloads. So that it was a small cluster, but we had customers on a lot bigger clusters. So problems we had were high response rates. We're talking about 10 to 20 seconds, about simply like Prometheus doing the request and then the metrics coming back. That whole time span was 20 seconds. On the one hand, that sounds like something that is not very nice performance optimized. Like, we can probably get more out of this. In addition, like this in terms of business, in terms of monitoring data, like having all your monitoring data 20 seconds late is a problem, because you might want to correlate that data with other systems. And if some are 20 seconds off and some are not, or some are 30 seconds off, correlating the two is very difficult. And that would be the power of Prometheus or any monitoring system, to correlate different data streams, which we really want to do with kube-state-metrics. So we want to reduce that number by a lot. In addition, running this on bigger clusters, we had quite a lot of issues opened about, like, how much memory does this actually use? How much CPU should I give it? So all of this planning is quite difficult. In general, we could optimize it, but also one goal was to stabilize, for example, CPU usage by a lot. So not have it be a very spiky workload, but instead being quite flat out. Right, so that's the problem statement. Now, this was all inside of SIG Instrumentation, so how do we do this? Well, of course, we use our monitoring system to optimize our monitoring system. So let's look at a couple of metrics that we want to use to optimize all of this, or the metrics that we want to optimize for. So the first thing is really scrape duration seconds. This is just a snippet. These I did later on after the performance testing, so I didn't have the bigger cluster available anymore. This is actually a super small cluster with a huge amount of config maps, not very optimized. But the graphs are pretty much very similar. You see very spiky return rates, like how long does it take for Prometheus to scrape. And that is difficult to correlate when sometimes your workloads, like, your metrics come back at like 6 seconds, and sometimes they come back at 3 seconds. How do you correlate that with other metrics? In addition, while we're at it, why not also optimize a couple of other things to make this easier to run, to operate. So for example, CPU usage was quite spiky. We'll go into why that is, mostly because, like, we have to iterate our cache every time and generate all the metrics. So CPU load is very spiky. Maybe we can optimize for that. And also, in general, memory would be nice to optimize in the long run. So these are the 3 metrics, pretty much, that we want to look at along the way. All right, so we can dive right into it. My graphs are a bit off, but anyways. Caching. The first thing, and probably the most helpful thing that we were able to do, is optimize the caching layer on kube-state-metrics. In general, Kubernetes is very nice as it gives us that client library and watch API, and we pretty much don't have to take care of cache invalidation, which makes this project a lot easier in general. So this is the old overview. You remember this. The API server notifies us of a new pod. We cache that pod, and whenever Prometheus comes in and wants to get the metrics, we iterate over our entire cache and then return the metrics. So instead, how about we get a new pod, we generate the metrics for that pod, and we cache the metrics. And then whenever Prometheus comes along and wants all the metrics, well, we return the metrics that we really have in cache here. That is a lot more optimized. That is, in the best case, like taking this memory chunk and simply shoving it into the network card or the network interface. That's the best case. Of course, that's not what's in the end happening, but very close to. All right, so this is all under the premise that probably more Kubernetes objects are going to change than we get scrapes in, so that Kubernetes objects actually change more often, but a lot of them stay the same while Prometheus regularly scrapes us. Okay. Cool. Make this more specific. Previously, we were keeping the Kubernetes object in cache. Now we keep the Prometheus object in cache. Now, how much did this actually help? This is on a 250 nodes cluster right now. I think we even, in the end, like it only matters how many objects you have on kube-state-metrics. It doesn't really matter like how many workloads or how powerful those workloads are, as it's simply like rendering text. So this is, I think 1,000 pods per node. So quite a lot of traffic for kube-state-metrics itself. And on the top, you see the red one is the old version. You see it quite spiky. It alternates between 2 seconds and 1.5. And then on the bottom, you see the new version, super stable. Yeah, keeping the same scrape durations pretty much all along. All of this cache logic, I already said, like Kubernetes Client Go is super helpful in that. It gives the idea, or the high-level idea of informers. Underneath that, you have reflectors. Reflectors, in the end, like let you watch a resource and update a store that you can define, and you can implement this interface that you see on the right side. And instead of using the normal store that would simply like cache Kubernetes objects, we implemented our own store, and that uses simply like metrics as in the cache. And we're being notified of new objects. We transfer them into metrics and then save those in our own cache. All the like cache invalidation notifications are coming from the reflectors, so not a lot of work on our side here. Cool. From caching on, we can dive into compression. On the top here, you have a snippet of the Prometheus metric exposition format. And this is simply one single metric. And you see here, kube-secret type, like that is super repetitive. And as an engineer, you would say, like, OK, let's take compression, and we save more than half of our network bandwidth in total. In general, like Prometheus moved off from a gRPC format into a text format with version 2. So hopefully we can still optimize on that. The previous kube-state-metric version would gzip all of this by default, as the Prometheus client library does that by default. But we wanted to play around with it a little bit and also add compression into the new version of kube-state-metrics. So different options were gzipping, standard Golang gzipping, and New York Times gzipping. New York Times is, they wrote a gzip handler library in the end, which sounded quite promising, so we wanted to try them all out. We haven't fully optimized for them, so for sure we could have done a better job, like tuning every single thing on the compression options. All right, so just to be clear, like we compress the metrics output and then send it over the network to Prometheus. That's the part we compress. So on the very top, we are right now looking at CPU usage. On the very top, you see the old version again. We'll go a little bit into why this is so repetitive. You'll see that once we see the memory graph. But underneath, you see two green versions, like the green, and then on the very bottom, a blue line. The two greens are the optimized kube-state-metrics version with gzipping. And, well, by surprise, like, it does use more CPU than the lower version. Of course, the lower version doesn't do gzipping, and yes, compression takes CPU. But hopefully later on, we'll see that our network is going to be way faster. Let's look in addition at memory. We had quite a big cluster, so the old kube-state-metrics version would just simply because it would, well, take way too much memory. You see where it's ramping up and then just being killed. That actually explains the CPU of the red line in the previous graph. But also now you see memory usage on the gzipping ones being slightly higher than the no gzipping. In general, being very stable, but you see them being a lot higher. And here I need to explain a bit, why does gzipping take more memory than no gzipping? Well, we can't really keep the gzipped version in memory, as we have our cache like structured as Kubernetes objects. For example, if a new pod or an updated pod comes in, we want to generate the metrics only for that pod, and then change the cache value for that pod and not for all of it. If we would change it for all of it, we would generate all the metrics every single time over the entire cache, and that would be super expensive. So what we actually need is we need access to like metrics of a single object. That way we can't keep a compressed version in cache, but we need to compress every single time. So that way you use or we use on kube-state-metrics more memory on the gzipping one. But still, like, this could all still be perfect for networking, so let's look at those graphs. In the end, like, scrape durations is like the total, like the network, how long does it take a network and how long does it use on both sides in terms of on our CPU. And again, you see the red line, like old kube-state-metrics version being killed. It's taking 0 seconds to scrape, well, because it's simply not there. Then you see on the very top the two green lines and then the blue line. The green lines, again, are gzipping enabled, and the blue lines are no gzip. Here you can see, like, while gzipping might have helped us in terms of the network, but it really didn't help us in terms of CPU time. So here, like, the blue line, the no gzipping really, like, sticks out as being the most performant one. And that was also our conclusion in the end. Well, first of all, like, with gzipping, we increase our size internally, like memory, our memory footprint. Then also, the saved improvement on the network is really not worth the extra CPU cycles that we waste on the compression itself, especially as we can't better compress. I'll go a little bit into detail how we could improve that in the future. And yeah, we have higher CPU utilization. So in the end, what you need to keep in mind, kube-state-metrics is probably very close to your Prometheus, so that way you're probably on a very high-performing network, so probably that doesn't matter. Now, maybe you have a lot of network congestion, so you might want to enable this. This is an optional now in kube-state-metrics, so maybe you want to go into that, maybe not. If you have more feedback on that on bigger clusters, I would be very curious. Right. Now, next to the caching and compression, we are in a very specific use case. This actually happened on Prometheus upstream. This is done by Björn from the upstream team. What we can do, what is quite expensive, is converting floats to strings. Of course, not if you do one, but if you do so many that you end up with 50 megabytes of metrics, you definitely want some optimizations here. And what we can do is we probably have default values. Like, we probably have a lot of zeros in our metrics, a lot of ones in our metrics. So what we really do is, like, check for those default values and render the strings a lot easier. That makes it a lot faster in terms of metric rendering. Then, in addition, I'll dive more into that in a bit, but what is also very important, if you want to be very specific about how you render your strings in Golang, you might want to look into Strings Builder. It doesn't give you so many options, like, for example, the FMT package, but it is a lot more efficient. In the end, like strings in Golang are immutable. That way, every time you change a string, you need to reallocate that memory. Instead, what we can do is we can use byte slices, which we can mute, and that we can address a lot better. So Strings Builder simply leverages on that point, which got us quite far. All right, so comparing all of that in a couple more versions, a couple more stats here. On the top, you see the old version. You have a scrape duration of 22 seconds. That was quite a big of a problem. We didn't get it all the way down to like insanity below 1 second, but a lot better for sure. CPU usage is one that is just normalized compared to the others. We have 2.5 gigabytes in memory as a peak, and then the amount of percentage that we spent in garbage collection. All of this was tested on a production cluster, actually by Björn at SoundCloud, which we are super thankful for, like to have some production workload on this. Then the next two versions optimize on the metric rendering itself, not on the caching logic. And here you see, for sure, an improvement on scrape durations, but still we generate all the metrics every single time Prometheus scrapes. So it's not a huge improvement. CPU usage got a lot better. That's mostly the use of Strings Builder and defaulting on float conversion. And then also memory we could reduce as, on the float, reusing buffers, one, and then also the float conversion got a lot more efficient. Of course, we spent less time in garbage collection. This reduced memory allocation by a lot. So that was also very useful. On the bottom two, you see the caching optimizations. Here, that is actually the biggest improvement, as I said earlier, for our specific use case. CPU usage dropped a huge amount because simply we don't need to regenerate all the metrics every single time. And also, like, memory dropped a lot, as like caching metrics is actually a lot more efficient than caching Kubernetes objects in our use case, as we're throwing away most of the data anyways. And again, garbage collection, hey, of course, we're not throwing away all the metrics, so garbage collector is really not that tough. And yeah, we save a lot of CPU cycles through that, as you saw earlier in the graphs. Right. All of this resulted in version 1.5. That was released, I think, this year, maybe January or something. Got good feedback, pretty much no bug reports, which I'm a bit surprised, but anyways, that worked quite well. 1.5. Now, for the next one, this is a community project, so we got a huge amount of new metrics coming in all the time. So a lot of stuff piled in for the 1.6. So we prepared everything for that, and I did a bunch of regression tests again, just to make sure we don't like mess up all the work that we previously did. And what I did is do a lot of profiling on this thing on, again, a test cluster with varying workloads, which was quite interesting. kube-state-metrics has a remote profiling endpoint, so this is super easy in Go to profile your applications. And wanted to dive into a couple of things that like stuck out for me and that might be interesting for you as well once you optimize some Go on Kubernetes. One is my profiles were like runtime grow slice was all over the place. And I was a little bit like, okay, grow slicing, maybe we can optimize for this. And I looked into runtime grow slice. This is simply the upstream like Golang core function. What in the end it does, it grows the capacity of the slice. For the people that don't write Go very much, like a slice is not an array. Arrays are fixed size at compile time, whereas slices are variable sized at runtime. So you can grow them. In the end, slices do use arrays underneath, but that's like an implementation detail. Okay, so I thought, we're spending quite a lot of CPU cycles in this growth slice. Why are we doing this? Can't we like pre-allocate more memory in advance? Can't we be more efficient on that? And what you see a lot, like we iterate through pods and we iterate through the properties of pods or config maps or ingresses and so on. And we really, like at the beginning, we allocate like an empty slice of metrics. And I thought, okay, I'll be really smart and, well, allocate a certain length, pre-allocate all of it, do the allocation at the beginning, and then iterate and simply insert it into that pre-allocated slice. We can't go with arrays because we don't know the size at the beginning. That would be super nice. Maybe that then could even stay on the stack instead of the heap, but at least like, this is a good start. Anyways, testing all of this, you can ignore the blue line on the bottom for now. You see the red one and the green ones. Those is on the one hand the optimized version, on the other hand the not optimized version. So pretty much this didn't help a lot at all. I dived a little bit deeper into the language itself, and what you can really see here is like growth slice actually grows by doubling every single time. Pretty much, there's a little bit more heuristics around it, but actually what we do is we don't grow slices so often. So this grows exponentially and simply like, it doesn't happen that often, so it's fine. And that way, my optimization didn't really help a lot. This is good to verify on your clusters whenever like you can just run the versions next to each other. Now I do want to go into the blue line on the bottom. After some more profiling, I saw strings to slice bytes stick out quite a bit. We wasted a lot of CPU cycles on this. And first thought from me was like, byte slices, come on, those are strings. Like that's just on the type system level. Like how does that differ in any ways? And as I mentioned earlier, well, strings are immutable, byte slices are not. To keep up that guarantee, imagine you have a string and you have multiple references to that string. And now that one reference changes that string or casts it into a byte slice. That way it has a mutable reference to it. It could mutate that byte slice, and thus the other reference sees a string which is being mutated, which is quite a problem, right? So in order to keep up that guarantee of strings being immutable, Golang actually takes the entire memory section and copies it. So that was super heavy on us, and I'll actually show where that happened. We were simply like stupidly caching the metrics as strings. And then whenever Prometheus came in, well, the HTTP library, the standard Go HTTP library, want byte slices. We had to convert the strings to byte slices, which is a bummer. And then lost quite a bit on that. So what we did instead, cache it at byte slices, as that is not the hot path. And then whenever Prometheus comes in, we can like simply render out those byte slices right away. Now this is actually the blue line at the bottom. We are looking at the CPU consumption here, and that saved us a lot for the 1.6 version. All right, all of this resulted in the 1.6 version. We released that one. Yeah, and that is the current version. You can check it out. All open source, all the, it's all pretty much like goes down from one pull request, so you can click through all of it. And yeah, I want to dive a little bit into the future of kube-state-metrics, maybe what we can do from a performance side. And definitely, this is also a slide where like this is probably over-engineering on the lower parts of this, but I'll dive into it anyways. First of all, like Frederic in the front here is working on sharding kube-state-metrics. Don't get me wrong, that's not the over-optimization. This is actually super useful on bigger clusters. What you can do nowadays already, you can shard based on Kubernetes types. But if you have a lot of pods and just one config map, like sharding on that is not super useful. So what Frederic instead developed is you can shard based on Kubernetes object IDs, and then you can distribute your shards, or you can load balance on your shards a lot easier. Then, in addition, Jimmy pointed me to heap escapes to look more into like when does stuff in kube-state-metrics escape to the heap? When can we not stack allocate? Stack allocation should be a lot more efficient and especially be a lot more efficient on the garbage collector. So there's some nice tooling on Golang around that, so I'll dive into that. Then also we could go further into memory alignment on structs. There's nice tooling around that, at least in the hot path. That might save us a lot as Go like allocates memory in buckets. So like small performance optimizations on the structs could push it into lower buckets, which should help a lot. Now this ... is the saying like, okay, this is enough. And then I think like the over-engineering would start with like exploring commutativity on gzipping. Maybe someone has experience, so I would very much appreciate your thoughts. But what we could do is we could, in the cache, keep the gzip versions and somehow like make use of commutativity of gzip so that it's still performant even though we only gzip parts of it. But yeah, that might be a tiny bit over-engineered. Yeah, that is the future of all of this. In general, maybe a takeaway is kube-state-metrics is a lot more optimized nowadays. So we had a lot like from upstream Prometheus, but also inside the Kubernetes community on this. But also, when you look at it from a different perspective, as I said, like as the alternative title from the talk, takeaway is, like, first of all, monitor your cluster and application. We have to say that as SIG instrumentation here. But also use your monitoring, of course, for alerting, but also use it for performance analysis. And make this available to your developers so they can debug regressions, they can run their software in different versions and can compare it over long terms. This was super helpful for me, sorry. And then last, as I showed you, like not every optimization is very helpful. And sometimes the Go memory model documentation actually gives a very good tip on this. Like if you must read on the Go memory model, so if you have to read this document to understand your code and understand the program of your program, you're being too clever, and don't be too clever. Yeah, that is it. Thank you very much for your attention. I think we have 3 minutes if there are questions. Otherwise, I'll stick around as well. Yeah.
Yep. Thanks for the talk. It's really good. My question is, have you ever used Go benchmarking tools? Because I can see you validate that on the via Prometheus, which is fair, and like it's ultimate acceptance test, which is good. But the problem is when you don't have this, even load that would, kind of test the thing. And did you find the Go bench useful? Did you use it?
So what we do in kube-state-metrics, actually at the very beginning, we made everything that kube-state-metrics talks to abstracted. So we built stubs for everything. And so what we can do is test kube-state-metrics with the Go benchmark tool entirely with anything around it. We did that both on like smaller scopes, so unit testing, as well as integration or kind of end-to-end testing in that version. All right, let's call it integration testing. So what we have now in our CI actually is our CI automatically checks out your patch and also checks out the master, runs the benchmarks over both of them, and then there's a really cool tool on this standard Go that compares the two and then prints it out. So every single PR we can like check, does this introduce any regressions?
Did you use it?
We do use it on the CI, yeah. Yes, actually, all of this, sorry, I should have mentioned this. Most of this stuff on Prometheus upstream, Björn was mostly using it, and that way I was like, yes, I need that as well. Yeah, good question.
Thank you, great talk. I'm wondering if you are still using the Prometheus client Golang library to expose metrics.
Mm-hmm.
Yes.
We don't. That was quite, that is definitely a big risk that kube-state-metrics went into, like going away to a more performant version of the client library for this use case. Like I'm not saying like the Prometheus client library is not optimized, it is way more optimized, but this is specific for our use case. So this is a different in some terms, a different code, but it tries to reuse most of the concepts that upstream does. But yes, we are a fork now in terms of Prometheus compatibility. Yes.
This is not a general purpose library, so
Yeah.
this is very much specific to the kube-state-metrics use case. Other questions?
All right, cool. Thank you very much.